Hello. Hello. Have you seen that I just posted the grades? No, you might be so interested in looking at them eventually. So average is 69, 70, something like that. Yeah, something like that. So not too bad, not too well. It's lower than last time. But I expected that because yeah, in person there's more honest. I'm going to be positive. There's more honesty in person than online. That's one thing. One thing I would say the person who graded it surprised me. Said maybe less than half of the class got just the question. Please transcribe the system of equations in matrix form. So this is, yeah, this I was surprised a bit. I thought it would be just you just you don't have anything to think about. You just transcribe it. So please fix this for the final. I'm really convinced that I'm going to ask a similar question because that's disappointing. Yeah, and more than that, you have to thank him. Well, so I already thanked him on your behalf. Why? Because I specifically wrote in the question, please make sure that this matrix is okay, because you have to make a bunch of computation with it, and if it's not, then it's complicated. And I said, okay, I think you can more or less look at the matrix they wrote and do for yourself all of the subsequent steps and make sure it works. But if it takes too long, you're allowed to just say, okay, it's bad, because it just takes forever. Well, he did his job well, and he just took whatever you wrote and did all the steps to give you half points there, half points there. So it's very nice. So yes, I'm going to ask you again to just transcribe a system of equation in matrix form. That shouldn't be too difficult. So, one thing is, so for the set question, so just the first question, how many elements do you have in a set that contains reals or rationals? Well, you have an infinite number of elements. So even though you put bounds on it, well, if you have 1/2, 1/4, 0.09999 or whatever, so you have an infinite number of elements in there. So that was something I've never said explicitly, but I just to help to make you think a bit outside the box about something else. Anyway, so 69 and 70 isn't all that bad either. So it means buckle up for the final, and it should be all right. Plus, you had less time. I think this was a factor. Okay, so today we finish chapter 8 and we start chapter 9. Chapter 9 is the final chapter. So we're almost done, but not quite, because it's a very long chapter. So it's all about optimization. Yeah, it's a good chapter. So, but just right before that, let's finish this. Oh, and by the way, also I have finished devising your third homework. I'm going to give it to you on Thursday. And yeah, so I made it interesting, which is not necessarily an easy thing for you, but yeah, it's I hope it makes you work a bit. So it's feasible. So if you're at some point you don't know what to do or you're stuck, email me. I'm going to give you hints. So the goal is to make everybody understand and work on the material. All right. So back to where we were. So implicit function theorem. So from a big picture, what's the implicit function theorem? It's just starting with some function that is in higher dimension. So here we have something that's connects value of z, x, and y. So here, just to for an illustration, I said it's something like a terrain where you have different altitudes, so 200, 220. And then what is the implicit function theorem? It's just the idea that you can decide that you cut this at some place like 220, and then what you're going to get is a slice which has some boundary there, and this describes a function. So we just want to say that we can describe this function. And what is important, I have said, essentially you can do that anytime the derivative of the function, say g, exists, and anytime you're not like just around the corner, because if you're just around the corner, then you cannot say it's a function from say x to y because it's perfectly vertical, so it's not a function. And of course, it's true only in some region of some points. So you could say you have a function that is around this point, for instance, and you can compute its derivative and stuff like that. But you can't say that like the whole thing is a function, because obviously now you have 2 points for every x, so that doesn't work either. So here's how you do it. So you just again set. So you set the value of z to some value there, 0 or whatever, and then you can describe properties with this. So you can compute the variable, the derivative, if you set dz equal to 0, for instance. So that's what we did there. And yeah, so it works as long as the derivative with respect to y is not 0. Otherwise, you're around this corner there, and you cannot find the derivative. So let me just formalize this really briefly. Where was that? Oh yeah, okay. More formal. Given a function, I'm still going to do it in three dimensions, but it can go to any dimensions you like. F of x, y, and z. And here, for instance, if you go back to what I had this expression there. So how you would define it, it would be something like, so from the last example. So that would be so I had this. So you just say that something like minus g of x and y plus z equals 0. So that would be your function equals f. F of x, y, equals 0. So that's what we had in the last example. And a note, more variables with, yeah, you can have more variables. Just it's the same thing. Yeah. So if there is a point, I'm just going to call it x0, y0. z0 such that so f of which is equal to f of x0 y0 equals 0. So if they obey your function, if this is on your line, so for instance, this would mean that I chose x0, y0, and z0 such that this point makes sense. I'm not, so for this value of x and this value of y, the value of z would be 200, for instance. If that's the case. Oh yeah, so I have multiple conditions. So one is this. One is that the derivative exists, fx of fy of p and fz of p. The partial derivatives of f at exist. And finally, the last condition, f of y, so the derivative with respect to y is not 0. Then that's all we need. Then an implicit function so you would say y equals f of x and z in the neighborhood of p that is bounded and as partial derivatives exists. Yeah, I'm just going to write this. So this is exactly the same thing as we did last time. It's just a formalization of this. So it's a three variable version of the implicit function theorem. So if you want to know the full theorem and all the little detail, you can see the textbook. So see. And so the goal is not to have excessive formalism. Again, what we care about is that the value of p makes sense. So f of x0, y0, z0 is 0. That they all have partial derivative with respect to each variable, and the partial derivative with respect to y is non-zero, then you can have a function that describes y as function of f of x and z. So I've already given some examples before, so but now I want to have two that are very useful for economics. Yeah, for example, economists like to have something that's super general. So we can say that what I'm claiming is true, it's true no matter what the shape of the function I'm using is, for instance. So that's very useful. So example, consider, and this is going to be useful for the homework. Consider an unspecified function g of x and a relation. So let's have g of x plus x equals y plus log of y. And now, so can we describe an implicit function from x to y? Well, yes. So consider point x0 such that. So this is our first condition. So it has to be the case that this is true. So x0 and y0 must verify this equation. Then we can specify that we can take the total differential and the total derivative. So the total differential is. So why don't I let you try to do better than last time and compute the total differential of this one? So here I'm not asking for a derivative yet, just a differential. Of course, it's not this, that's just my template. Somebody wants to take a crack at it? No, no takers. What's my? Yeah, go ahead. That's great. We're here to. Yeah. Um, Supposed to yes, that's dy and 1/. So note the following. So I'm making a difference between the value of the point there, x0 and y0, and dx and dy. Dx and dy are just small changes in x, small changes in y, but these have to be at the specific value. So great job, thank you. I didn't even talk about g prime of x, but that's exactly what you said. So this is exactly it. So of course, as long as g prime of x exists, and then the total derivative dy dx at this point, x0, y0, would be this. So that's quite easy to do. I just, again, take the terms everywhere. So, all right, so let's fit these two. Then and then, of course, as long as so y1 plus 1/y0 is non-zero. So this it's bad if y0 is -1. All right, so this is how you would do it. So now, as if you know some properties of G prime, you're good. So for instance, if you know that x0 is positive and that G prime is positive, so then you know that this derivative is positive. Sometimes that's all you care about. You just want to say, I know this is positive. All right. So yeah, I'm going to give you a nice quiz. Yeah, that one. On differential and derivative and all of these things. So you can do it. Plus some, you're going to have to do some of them in the TA session. Some economic application. The consumer problem. Here I have a picture, I think. Here it is. So this is, yeah, so under subject budget constraint. So you may remember this from some economic class you have taken, I hope. So what did we learn about this problem? Well, so do you remember something about what happens at the optimum? Yes, no, maybe. So the consumer can consume good 1 and good 2, quantity x1, x2. This is the budget constraint. This is the utility function. So let me just write it down. So it's more. There are two goods. The budget constraint, yeah, the consumption of one and two, the budget is P1 x1 plus 2 x2 plus n. So yeah. So I'm not going to care about the fact that it could be inside the budget line. Now we know that the consumer is going to consume in the boundary. And let's have a utility function. So is u of x1, x2. And no need to say anything else. And now, do we know something about what the consumer is going to do? Or is it too far back? Are you taking some macroeconomics class this semester? Or? Yeah, macro, yes. No, yes. I didn't understand your answer, but I'm going to assume that at least you remember some of the earlier micro class. So we know that at the optimum, the marginal rate of substitution must be equal to the ratio, the relative prices. So why do we know that? Well, we know that the budget line is going to be tangent to an indifference curve. So yeah, I shouldn't have written that actually. That's like the punchline. So imagine I didn't write this. So yeah, an indifference curve must be tangent to the budget line. So how can we find this? Well, this budget line is, well, it's an easy function. We already know what it is because we can just write x2 as function of x1. But here we have some utility. So the utility is some value, and that's function of x1 and x2. So I have an infinite number of indifference curves. But what I know is that this is budget line, indifference curve is just like chopping my big utility function at some value of u that is constant. So du equals 0. So it's like using the implicit function theorem. So so the only thing we need to do is the slope of the indifference curve of the utility function, the indifference curve, and the budget line. All right, so let's start with the budget line. That's an easy one. So we have that this equals to this. Right. So here I'm expressing it this way. And then the slope, what is the slope? It's just explicitly said, it's dx2, dx1. And then what I can say is, so I'm going to specify that the budget is fixed, so I cannot change my budget. If I can find, so this is 0, it's constant, and here I have just d minus p1 over p2. And now let's express let's find the slope and indifference curve. So we have this. Yeah, I think I should write it this way. U is U of x1, x2. Just to say that this is U is some other value that's a function of x1 and x2. I know that so some of you may not like the fact that I use U as a value there and U as a function there, but yeah, we do that all the time. So total differential. So I'm going to get that du equals to u1 x1 x2 dx1 plus u2 x1 x2 dx2. So this is saying if I want to change my utility, what can I do? I can either change the consumption of good 1 or change the consumption of good 2. How will they affect my utility? Well, if I change x1, then the impact on u will depend on the derivative simply of du dx1 or u1. And then, of course, on an indifference curve. The utility is fixed. So du equals 0. So then I get 0 equals this. So let me rewrite this. I have a minus sign. And here I could say that, so I'm taking the derivative, assuming that du. Right, so this is what I got there. So this is dx1, dx2 time, assuming that du is equal to 0. That gives me the slope. And dx2, dx1, assuming that the budget is fixed, give me the slope of this curve there. And then, so if the slope are the same, so I get or that. And yeah, this is the punchline. So that the marginal rate of substitution U1 x1 x2 divided by U2 x1 x2 must be equal to the relative prices P1 over P2, right? So that is some way you can do that. So you have something similar to do in the homework. And last time they had something to do similar in the exam, and I had not explained a lot, so that wasn't super well successfully done. But yeah, still they managed to do it. Okay, so again, here I have a function of three variables, u, x1, and x2. I take a slice of it, I get indifference curve, and what I care about is at the optimum, the slope of the indifference curve is equal to the slope of the budget line, and this is what gives me this result there. That u1 u2 equals to p1 over are you all good with copying stuff? Yeah. So I think I'm done with this chapter. Yeah, done with the chapter. Okay, so yeah, that was a rather long one, but yeah, I think all of these stuff, all these things are useful. Okay, no questions? Otherwise, we jump on chapter 9. Optimization. Sadly, with a single variable. So normally you would just see optimization on in the next class, so the next in the series. But few of you are for a few of you it's like the last mathematics class I think that you're taking. So that's why they include the optimization with a single variable inside the curriculum of this class. But yeah, as you can see, we can do many things with many variables, even if we don't really formalize all of everything that has to do with with the multiple variable case. So yeah, it's quite useful. Okay, so I would say end equilibrium analysis. So why do so let me, this is an important chapter. So why do optimization? Well, this is a small motivation for it. So because economics, microeconomics especially cares about agents that optimize stuff. That's our founding paradigm or founding assumption is we think that people are smart in general and they try to do their best in their lives. So that's what we use to understand their behavior. Is that by optimizing agents? For instance, consumers maximize utility, firms maximize profit, or minimize cost. So these are all problems that you've seen. And second, very important reason why we study this, because when we fit models, econometric models, statistic. So we optimize all the time. So if it's a general method of moments, you minimize error. If it's maximum likelihood, you maximize the likelihood that your data is the right data to observe the model that you are claiming you're having. So it's always a question of so it's M estimators is yeah, no, let me not include too much econometrics in this, but yeah, there's a whole class of estimator that's called M estimators in the econometrics, which encompass most of what we care about, which requires optimization. Okay, so the main vocabulary, so an optimization problem. An objective function. The goal is to find a maximum or a minimum. Both goal extrema. Yeah, so I'm not sure if Latin is necessary there, but yeah, I'm going to use the terms maximum, minimum, extremum, maxima, minima, extrema. So it's just the plural of it. And the extreme value can be local or global. So it depends on the problem. So here I have many drawings from the book. There's one. Okay. So A, B, and C are what? A, B, and C. So assume that everything that you need to see is what you see on the graph. Of course, maybe the function continues later, but yeah, assume that everything we care about is here. So what are they? Minima, maxima, local, global. If you just use your intuition, I'm sure it's the right answer. There's no trick there. It's or maybe it's too easy and you wouldn't be bothered to answer. Okay, well, so to be a minimum, it has to be the smallest possible value that the function can take. So A is at the minimum, B is at the minimum, and C is at the minimum. And to be a maximum, it has to also be the maximum value it can take. So again, A, B, and C are maximum. And they are global minima and global maximum because you don't have any other place in which the function, so you need some curvature for having minimum or local or minimum or maximum. So A, B, and C are global minima. D is what? Yes. And is it global or local? Yes. And finally, E is maximum or minimum. Yeah. Global or local? Local. Finally, F is local minimum. So you can see that, so these things were more familiar when the function is can be derived and is smooth. But this thing is also possible, in which case you don't have a derivative, but you still have a minimum there because for whatever reason I decided that, or the book decided that the function was drawn up to here. So for all we can see, that's a minimum. Just it cannot be derived. And ABC are, if it's just a function is constant, then yeah, so they are the only value that the function can take. So property of if a relative um, extremum of a function occurs at some value, so I'm going to say, yeah, so okay, I'm going to say that the function is f. Then two things can be the case. Then either one, the derivative is zero, so that's what we're more familiar with. Or second possibility, so the derivative does not exist. Okay, so if I were to ask, in which case do I have a derivative that is zero, and in which case do I have a derivative that does not exist? You have to remember your derivatives. So what's the derivative at b? So if I have f of x here, and the derivative df y equals f of x, so the derivative here is 0, at c it's 0, at e it's 0, at f it's 0, and it doesn't exist at 2 points, at a and at d. Why? Because a stops there, and yeah, just my domain is finishes here, and d is the same thing, the domain finishes there. So that's what did I say? B, C, E, and F. And point A and point D. And why is that the case? Well, consider sitting anywhere else. So for instance, here, there is some, the derivative exists and it is positive. So can this be a maximum? No, because if the derivative is positive, I can just go slightly to the right and the function is going to be bigger. So it's not a minimum. Can it be a maximum? Well, no, because I can just go slightly to the left and the function is going to be lower than that. So if the derivative exists and it is non-zero, then it cannot be an extremum. So if if f prime is 0, exists, isn't 0, it cannot an extremum is 0. Um, First derivative test. So to check whether you have a maximum or a minimum, what do? You take the derivative and you set it to 0. So here, let me show you. That one is like redundant with the other ones. It's because the derivative doesn't exist. So yeah, it's not super helpful. I'll go with that. So, oh yeah, so yeah, no, that's rather yeah, that's for later. Something that I wanted to say. So f prime return 0 that if increase 0. Yeah, maybe that's putting it in too many words, but smaller than 0 means that the value of f tends to decrease at x0. So that's why it's not a maximum or not a minimum. if first derivative of a function f of x at x is 0 is prime x equals 0, then the value of the function then will be relative minimum, relative maximum if f prime of x changes its sign from positive to negative. So that's point D. Because here the derivative is positive, 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 then it's 0. We know we have an extremum, and then it becomes negative. So in that case, you know that probably the maximum was obtained exactly at point D. So of course, we have a relative minimum. If f of x changes its signs from negative to positive. So that's point C. And is that all? Are we sure that we can either have if the first derivative is 0, then we are sure to have a maximum or a minimum? So this is not a trick question, but a question that requires you to think a bit about what might be going on. If I'm asking the question, there's a risk that the answer is no, but you have to tell me why. No idea. So let me give you a hint. So if I have f of x equals x cubed, then f prime of x equals 2 squared. So f prime of 0 equals 0. Oops. So is 0 a minimum or a maximum or something else? You have an answer? No idea. Well, let's just look at what this looks like. So, this is what I have there. So yes, the derivative is 0, but it's neither a maximum nor a minimum. It's what we call an inflection point. So the derivative was getting smaller and smaller and smaller, but as soon as it gets zero, then it starts to increase again. So yeah, that's a special case. So it means that if you have an extremum where, so either you have don't have a derivative, or if you have one, then it's zero. But if the derivative is zero, it doesn't mean you have an extremum. In that case, you wouldn't have one. Copy that. It's a nice. So third condition, then what we have is not an extremum. So it can be a relative maximum, a relative minimum, or just not an extremum at all. If f prime of x has the same sign on both the immediate left and the immediate right. So in that case, x0 represent an inflection point. The point where okay, yeah, that's introducing some stuff there, but we're getting back to that later. So when the second derivative changes sign. So more on that later, so do not worry. Okay, so this is this example. So just some vocabulary again, in case you get that sometimes. Stationary point. Sorry. So if prime of x0 is 0, then x0 is called the critical value. F of x0 is called the stationary value of the function. and the point f of x0 is called the stationary point. I never learned that, so I should maybe, but as long as we know what we're talking about. So critical value is something I use quite often, but stationary point. So generally, I'm going to try and give you as many detail as to what I'm asking you to do. So I'm not going to ask you questions like, what is a stationary value? So don't care. All right. Something you are going to hear a lot. So for a local extremum, necessary condition, sufficient condition, does that ring a bell or not? Yeah, no. So condition f prime of x is a necessary condition yeah, where at x0. Yeah, that's more where f prime of x0 exists. So that's more precise. The condition f prime of x0 equals 0 is a necessary condition. So what we see is if there is a derivative, then it is necessary that it is equal to 0. But then that's a necessary condition for having an extremum, but it's not sufficient. So there are other conditions if you want a maximum or a minimum. So you have other conditions. So given one, so the change of derivative sign can serve as a sufficient condition for a relative maximum or minimum. Yeah, and then yeah, this makes more sense. Yeah. All right. Yeah, no, it makes sense. Okay. So again, so here, if the derivative is 0 and there's a change in sign from positive to negative to positive, then this is sufficient to say it's a minimum, a local minimum. And if it's there's a change in sign from positive to negative of the derivative, then this is sufficient to say that you have a maximum. So this is more or less what I said. Yeah, okay. Yeah, I have an inflection point, I think. Yeah. Here, example, an inflection. So here it's positive here. So even though this is the case, you need the second condition to be sure. So almost done with the definitions and everything. So a relative extremum must be a stationary value but a stationary value maybe either maximum or inflection. All right, so this is for, so lastly, before leaving, small example. F of x equals x cubed minus 12x squared plus 36x plus 8. So how do I find the local minimum, maximum, everything? What's important? So we just said that what is really, really important is the first derivative. So we want to know if where the first derivative is equal to 0. So what are we going to do? Well, the first step is to just so to find the extrema, or the, let's just see this for now, the stationary point. F prime of x equals to square minus 24x plus 36. Oh, yeah, of course. And set to 0. And then, so we just need to solve this quadratic equation. So finding the roots. So x is going to be this. So this is equal to so that's divided by 6 everywhere. So that's 4 plus or minus. So that's two possible values. So 2 or 6. All right. Then let's just confirm that this is the case. I have 2 minus 12x squared. Plus 36 times x. And then plus 8. Okay, so what did we have? 2 and 6. Yes, so 6 is a minimum and 2 is a maximum. Okay, so we're going to continue here next time. And I'm going to post the exercises and yes, so have a nice.